Think about how instantly a smell can trigger a memory or warn you of danger. Our noses are powerful, but they're also easily fooled, right?
Right. They get tired, sometimes put us in harm's way.
Exactly. So what if we could build a better nose? One that's, objective and never gets a cold?
Yeah, that's the idea.
Okay, let's unpack this. Today, we're diving deep into electronic noses. It's this fascinating tech twist on our own sense of smell. We've got a stack of research here, and we're going to really sniff out how these things work, what gases they can analyze, and, well, the surprisingly diverse places they're actually making a real impact already.
And what's fascinating right off the bat is why this technology even exists. I mean, our human senses and the traditional lab methods for sniffing out gases, they definitely have their limits.
Totally.
Imagine relying on a panel of people to judge the freshness of fish day in, day out. It's subjective. It's costly.
And probably not the most pleasant job either.
Yeah, probably not. Then you have lab techniques like, say, gas chromatography and mass spectrometry. Super precise, yeah, but they can be slow, expensive.
And you need a PhD to run them, practically.
Pretty much. So the big push has been for something faster, cheaper, portable, something anyone could use to analyze the air around us.
Exactly. So in this deep dive, we're going to trace how scientists went from those huge lab machines to these, well, electronic sniffers. We'll explore what makes them tick, the sensors, the processing, the sort of clever ways they identify smells.
And we'll also look at why they're better in certain situations, where they still have room to grow.
Yeah, and all the cool places you're starting to see them pop up. Our goal is really to give you the straight story on this tech and what it could mean down the line.
Sounds good.
So where did this whole quest for a super sniffer really start in the science world?
Well, if we step back a bit, the challenge with basic gas sensors is they often just tell you a gas is present, not which specific one.
Right, just something's there.
Exactly. But to really understand an odor, is that fish gone bad or is it just a different type of fish? You need to identify the specific molecules.
Makes sense.
And this need led to some of the early analytical techniques. It's interesting, actually. Some of these were almost like the first, maybe clunky versions of electronic noses.
Right. And the big names that probably come to mind are gas chromatography, GC, and mass spectrometry, MS.
Those are the classic ones, yeah.
For those of us who maybe skipped that day in chemistry lab, can you give us the simple version? How do they work, and why were they kind of the forerunners?
Okay, sure. Think of gas chromatography, GC, like a tiny obstacle course for gas molecules.
Okay.
You push a gas sample through a really long, thin tube, a capillary column that has a special coating inside. Different molecules interact with this coating differently. Some stick more, some less. So they take different amounts of time to get to the end.
So they get separated out based on how long they take.
Precisely. That separation lets scientists figure out what's in the mix. And mass spectrometry, MS, is different. It's more like a super sensitive scale for gas molecules.
The scale?
Yeah. It ionizes the gas, gives the molecules an electrical charge, and then it measures the mass of those ions. So based on the mass, you can identify the molecule.
Gotcha.
And when people started using MS with computers to recognize the patterns of different gas molecules, some folks did start calling it an early electronic nose. Though others were like, no, that's just good old MS.
A bit of a debate there. So GC sorts by stickiness, MS identifies by weight. Okay. What about ion mobility spectrometry, IMS? That sounds pretty high tech.
It is pretty cool. IMS also ionizes the gas sample first.
Okay.
Then it sends these charged particles, these ions, dripping through a tube with an electric field. Now, the speed they move at depends on their size and charge. Smaller, nimbler ions zip through faster.
Yeah.
So by measuring the time it takes for different ions to reach a detector at the end, you get the spectrum. It acts almost like a virtual sensor array.
A virtual array?
Yeah.
How so?
Well, it's like having a whole team of sensors where each one responds slightly differently based on how quickly the ion moved through the tube.
I see.
Now, analyzing really complex samples can be tricky because ions can bump into each other, mess things up a bit. But there are clever algorithms now that help sort out that data.
And how does it compare to MS data?
It's different. MS gives you more of a snapshot of different masses present at one time. IMS gives you a signal that sort of builds up over time as different ions arrive.
Okay, so different ways to pull apart and ID gases. Were there any other early tech noses floating around?
Yeah, there was near-infrared, or NIR spectroscopy. That works by shining infrared light through a gas sample. It measures how much light gets absorbed at different wavelengths. Since different gases absorb light at specific wavelengths, you can figure out what's there and how much.
Could that be an eNOS?
Well, you could theoretically use NIR with pattern recognition like an eNOS, but it mostly just stayed in the category of portable analytical tools. It didn't really catch on commercially as an eNOS per se.
I see.
Then there's pulse spectroscopy. That's a newer kid on the block. It uses a single solid-state sensor to create a kind of unique fingerprint, a spectroscopic trace of volatile compounds.
Just one sensor.
Yeah. It's fast, and it has the potential to be really small. It could offer similar identification power to mass spectrometry, but in a much tinier package.
Wow. Okay, so it sounds like scientists were already thinking creatively about gas analysis even before the term electronic nose really became, a thing. But with these established techniques like GC and MS around, what was the real push? What problem were they really trying to solve by creating what we now call an electronic nose?
Well, think about the practical side. GC and MS, incredibly powerful, yes, but also expensive to buy, to run.
Right.
You need highly trained people to operate them, to interpret the results. And the analysis often isn't immediate. You might wait hours or days.
Not ideal for, say, checking food on a production line.
Exactly. There was a clear need for something more user-friendly, devices that could quickly, cheaply analyze the air for these volatile compounds, and crucially, devices that could be used by people who weren't lab experts.
So portability and ease of use were key.
Absolutely. Maybe even for continuous monitoring in different places, online or off-site. And getting consistent, reliable results was huge, too. Repeatability and reproducibility, getting the same answer for the same smell every time, even on different machines, that was a major goal.
That makes perfect sense. So when did the actual term electronic nose get coined, and what's the core idea behind it?
The term electronic nose really took off thanks to a researcher named Julian Gardner back in 1988.
Okay.
And it became much more widely recognized after a NATO conference in 1989. Since then, there's just been a ton of research globally into instruments that use arrays of sensors.
Arrays, so multiple sensors.
Yes, that's the key insight. Instead of trying to build one super selective sensor that only responds to, say, ammonia and nothing else.
Which is probably really hard to do anyway.
Exactly. Instead, you use a team of sensors that are only partially selective. Each sensor in the array will respond to a whole range of different volatile compounds, but crucially to varying degrees.
Ah, so they each have their own little opinion on the smell.
Kind of. By looking at the unique pattern of responses across the entire array, you can identify complex odors that no single sensor could possibly recognize on its own.
So the definition would be something like?
A good working definition is an instrument which comprises an array of electronic chemical sensors with partial specificity and an appropriate pattern recognition system capable of recognizing simple or complex odors.
Partial specificity and pattern recognition. Got it. So it's not about one sensor screaming, aha, that's fish, but more like the whole chorus of sensors creating a unique smell signature.
That's a great way to put it, a smell signature.
And where did this idea of using a team of less selective sensors actually come from? Was it inspired by biology?
There was definitely inspiration from biology, but also from early chemistry studies. Research looking at how different odor molecules interact with materials through, redox reactions.
Okay.
Or how they change the electrical conductivity of certain materials or affect electrical potentials on surfaces. Scientists realized that different chemicals produce different patterns of responses across different materials.
So they saw these patterns emerging naturally.
Right. And there were also efforts even then to get more information out of a single sensor by, say, making it work in different ways dynamically, like rapidly changing its temperature and seeing how its electrical properties changed over time.
Clever. Trying to squeeze more data out.
Exactly. The underlying goal was always to extract more detailed information about the gases present than just a simple yes or no.
Now, when we talk about these sensor arrays, the natural question is, how many sensors do you actually need? Is it just a case of, packing in as many as possible? More is better.
Yeah, that's a logical question to ask. And you might think, intuitively, that having lots and lots of the same sensor would make the whole system more sensitive. There's actually some theory behind that sensitivity improving with the square root of the number of sensors.
Oh.
But in practice, you hit diminishing returns really quickly. Adding more identical sensors doesn't give you that much extra benefit after a certain point.
So it's not just about sheer numbers.
Not at all. The real power comes from having a diverse set of sensors, sensors that respond differently to the different chemical characteristics of the molecules you're trying to sniff out.
Ah, okay. So it's like building a team. You want different specialists, not just 100 quarterbacks.
Exactly. That's a perfect analogy. Using too many sensors that are essentially telling you the same thing, that are highly correlated, can actually just add noise to the system.
Makes it harder to tell things apart.
Right. It can reduce the differentiation power. So there's definitely a trade-off between the size of the array and the complexity of processing all that data.
So smaller arrays can still be effective.
Oh, absolutely. Even a small number of well-chosen sensors can be very powerful. There's research showing, for instance, that just 3 specific sensors can identify not only that there's a fire, but the type of fire and what stage it's in.
Wow, just 3.
Yeah. The key is that an effective array is designed with a specific purpose in mind. You choose sensors that will have different reactions to the target molecules you care about, separating them based on their chemical response differences.
That makes sense. You wouldn't just throw every tool in your toolbox at every problem.
Right.
So how do you decide which sensors to include in an array for a particular job?
That selection process is really crucial, and it depends entirely on what you're trying to detect. You need to pick sensors that will, first, actually respond significantly to the substances you're interested in.
Okay, they need to notice it.
Right. And second, they need to respond differently enough to those target substances so you can tell them apart from each other, and also tell them apart from any background smells or changes in humidity or temperature.
So you can't just grab every sensor type off the shelf and stick them together.
Definitely not efficient. Just throwing in everything available isn't the way to go. Statistically, people have estimated that even a small array, maybe 6 carefully selected sensors, could theoretically distinguish up to maybe 100 different odor patterns.
6 sensors for 100 patterns. That's pretty good.
Yeah. In reality, most commercial electronic noses you see typically have somewhere in the range of, say, 4 to 32 sensors.
Okay.
And one other thing to consider, sometimes the sensors in an array can actually influence each other. The order matters. For example, a hot metal oxide sensor might slightly oxidize the gas sample before it reaches the next sensor downstream.
Ah, so the first sensor could change what the second sensor smells.
Potentially, yeah. Or a sensor designed to detect flammable gases might actually consume some of the sample. So array design needs to account for those kinds of interactions too.
Okay, so we have the sensor array doing its thing, collecting all this data, these electrical signals. But that raw data is just, well, a bunch of numbers, right?
Pretty much, yeah. Just signals.
How does the electronic nose actually smell a pattern in that? That's where the signal processing comes in, I guess, the brain of the operation.
Precisely. The pattern classifier, or pattern recognition system, is the second absolutely essential part of an electronic nose.
Right.
It takes those patterns of electrical signals coming from the sensor array and compares them to patterns it has learned from known smells or odors.
Like facial recognition, but for smells.
That's a really good analogy, yeah. An ideal pattern recognition algorithm needs a few qualities. It needs to be fast, obviously, easy to train with known samples. It shouldn't need a huge amount of computer memory.
Okay.
It should be reliable, even if the sensor data is a bit noisy or imperfect. It should ideally tell you how confident it is in its identification.
Like, I'm 95% sure this is coffee.
Exactly. And of course, it needs to be accurate.
Makes sense. And are these smell recognition programs just looking at, say, the peak signal from each sensor? Or is it more sophisticated than that?
It's getting more sophisticated. Increasingly, researchers are looking not just at the peak height, but at the way the sensor signals change over time when they're exposed to an odor. We call this temporal data.
Temporal. So time-based.
Exactly. And this is actually much closer to how our own biological noses work, right? We don't just take one big static sniff, we sniff dynamically.
Yeah, that's true.
And studies have shown that the shape of these time-based responses, how quickly the signal rises, how it plateaus, how it falls off, can often be more stable and reproducible than just looking at the maximum signal intensity.
Interesting. So the dynamics of the smell response matter.
They do. Using this temporal data can really improve the accuracy of identification, and it might even help us quantify things better, figure out how much of a particular substance is present.
So it's not just a snapshot of the smell, but more like watching a little movie of how the sensors react over time.
That's a good way to think about it.
But that must create a lot of complex data to analyze.
It absolutely does. The raw signals coming off these sensors can be quite complicated. They're influenced by all sorts of things: how fast the gas is flowing over them, the specific chemistry of the odor molecules, how they diffuse and react within the sensor material itself.
And environmental factors too, I bet, like temperature, humidity.
Big time. Temperature and humidity can have a huge impact. So to handle all this complexity, you need really sophisticated pattern recognition software. Honestly, developing and refining these algorithms, these classifiers, has been a major focus in the electronic nose field for years.
Okay, so what are the typical steps involved? How do you go from that messy, raw sensor signal to actually recognizing an odor?
Well, the first step is usually pre-processing. You have to clean up the raw signals first.
Like noise reduction.
Exactly. Things like normalization, adjusting the signal so you can compare sensors fairly, even if one is naturally more sensitive than another. Baseline correction, accounting for any slow drift in the sensor signal over time. And yeah, noise reduction to make the real signal clearer. It's actually quite similar to the kind of pre-processing you do with data from MS or GC.
Okay, clean up the data first. Then what?
Then you apply various chemometric techniques. That's just a fancy word for using statistical methods on chemical data. Things like principal component analysis or PCA, that's a really common one. It helps simplify the complex multidimensional data from the array and often lets you visualize the patterns in, like a 2D or 3D chart. Makes it easier to see if different smells are clustering together.
So PCA helps find the most important variations in the data.
Right. Then there's cluster analysis, which directly tries to group similar smell signatures, similar response vectors, together based on how dissimilar they are, often using something like Euclidean distance in that multidimensional sensor space.
Grouping the smells.
Yeah. And discriminant factorial analysis, or DFA, is another one. It specifically looks for the variables, the sensor responses, that are most useful for distinguishing between predefined groups of smells.
Okay. And you mentioned specific algorithms earlier, too.
Yes, beyond those general approaches. Early electronic noses often use something called K-nearest neighbor, or KNN.
KNN.
Yeah. It basically compares a new unknown smell signature to a library of known signatures it's already learned. It then classifies the unknown smell based on what the majority of its nearest neighbors in the library are.
Simple enough.
Relatively. More advanced multivariate techniques like linear discriminant analysis, LDA, and partial least squares, PLS regression, are also very common now. PLS in particular is a powerful technique used a lot in analytical chemistry for calibration, figuring out concentrations.
Okay. And what about AI? Neural networks?
Definitely. Artificial neural networks, or ANNs, are used quite a bit. You have supervised ANNs, which need to be trained on labeled data. You tell it, this pattern is coffee, this pattern is smoke. Examples include backpropagation networks or fuzzy ARTM maps.
Train networks.
And then you have unsupervised ANNs, like self-organizing maps, SOMs, which can find natural clusters or patterns in the data without being told what the smells are beforehand. They sort of figure out the groupings themselves.
Which type is usually preferred for e-noses?
Generally, for e-nose data, the trained supervised techniques like CDA, Fisher discriminant weighting, FW, ANNs, or radial basis function, RBF networks, tend to give better classification results once they're properly trained.
So it's a mix of classic statistics and some pretty cutting-edge machine learning going on under the hood.
Absolutely. It's a very active area of research.
Now, once you have these algorithms ready, how do you actually teach the electronic nose what's what? You mentioned training. It sounds like teaching it a new language of smells.
That's exactly right. Calibration and training are critical. Just like any measuring instrument, an e-nose needs calibration to understand the magnitude of the sensor responses and the relative magnitudes across the array.
Okay.
But for the recognition part, it needs training. This involves repeatedly exposing the sensor array to known smells, specific chemicals, or mixtures, usually at different concentrations.
So you give it lots of examples.
Lots of examples. Sometimes you even vary the order you present the smells in. The system carefully records the unique pattern of sensor responses that smell fingerprint for each of these known examples.
And stores them away.
Exactly. It builds up a library of these response patterns in its memory linked to the identity of the smell.
So you're basically creating this reference library of smells that the e-nose can then compare against later.
That's the goal. The whole point of training is to configure the recognition system so it can uniquely classify each chemical or odor you've trained it on. Then, when it encounters an unknown smell later, it generates its pattern, compares it to the library,
Finds the closest match.
finds the closest match, and boom, automated rapid identification.
That's pretty neat. Can it recognize things it hasn't been trained on?
Sometimes to a degree. A well-trained e-nose might be able to recognize parts of a smell, like certain functional groups or chemical building blocks, even in substances it wasn't specifically trained on, by finding similarities to patterns in its library.
Interesting.
But it's really important to remember an electronic nose typically identifies smells by comparing them to what it has learned. It doesn't usually give you a complete chemical breakdown, like this air contains 10 ppm of compound X and 5 ppm of compound Y.
It's more about classification and comparison.
Exactly. Its real strength lies in distinguishing subtle differences between complex mixtures, often mixtures that are hard to analyze otherwise.
Okay, so we've got the sensor sensing, the software processing, recognizing, and the training teaching it what's what. Now let's talk about the actual physical device. What does an electronic nose look like? What are the main bits and pieces?
Yeah, the hardware. A typical electronic nose has a few key modules. Different people might slice it slightly differently, but generally you have, first, a sampling system.
To get the smell in.
Right. It draws in the air or gas you want to analyze, maybe pumps it, filters it, and delivers it to the sensors in a controlled way.
Okay.
Then, obviously, you have the array of chemical sensors themselves, the nose part.
The core element.
Then there's the data acquisition and control electronics. This part measures the signals coming from the sensors, converts them to digital data, and manages the whole process, timing, temperature control if needed, etc.
The interface?
Kind of. And finally, you have the computer, usually with the pattern recognition software we just talked about. That's what analyzes the data and ultimately identifies the smell or classifies the sample.
So sampling, sensors, data acquisition, and the analysis software. Makes sense.
Pretty much. You need the hardware and software for sampling, analyzing, and reporting the result.
And when it comes to the sensor array itself, are there different ways those are put together? Different philosophies?
Yeah, there are. Within the array, like we said, you want sensors that have different sensitivities to the various gases you might encounter, both the target gases and any background stuff.
Diversity is key.
Right. You can achieve this diversity in a couple of ways. You can use what's called a homogeneous array.
Homogeneous, meaning?
Meaning all the sensors are from the same basic class or type, like all metal oxide sensors, but they're slightly different variations. Maybe different metal oxides are doped differently, so they have different response characteristics.
Okay. Variations on a theme.
Exactly. Or you can use a heterogeneous array.
Which should be?
Mixing completely different classes of sensors together, like putting some metal oxide sensors next to some conducting polymer sensors, next to maybe a SAW sensor.
A mixed bag.
A mixed bag, yeah. Interestingly, most of the electronic noses you see commercially actually tend to use homogeneous arrays, often based on metal oxides. But heterogeneous arrays offer potential advantages in terms of broader sensitivity.
Okay. And are there sort of broad categories of sensor types commonly used? You mentioned metal oxides and polymers.
Yeah, a simple way to think about it is often dividing them into hot sensors and cold sensors.
Hot and cold, based on temperature.
Exactly. Hot sensors are mainly those semiconductor metal oxide gas sensors, like MOS sensors, which typically need to operate at elevated temperatures, sometimes hundreds of degrees Celsius.
Okay.
Cold sensors include things like conducting polymers and those acoustic wave sensors SAW, surface acoustic wave, and BABO, bulk acoustic wave devices, which generally operate at or near room temperature.
And they have different pros and cons.
Definitely. They differ in things like sensitivity to different compounds, selectivity, long-term stability, how quickly they respond and recover, power consumption — hot sensors obviously use more power — and cost.
And the heated metal oxide ones are common.
Very common. Heated metal oxide, or HMOX, sensors are widely used. By tweaking the sensitive layers they're made of, often things like tin oxide, zinc oxide, tungsten oxide, maybe adding catalysts, you can get a really wide range of different response behaviors from them. There's a huge variety of, say, tin oxide sensors available.
It's lots of options within that one category.
Huge diversity. And the same is true for other sensor principles, too. Ultimately, the best sensor choice really depends on the specific application, what smells you're trying to detect. Manufacturers usually provide guidance on that. Ideally, you want every important compound in the gas mixture to cause some kind of response on at least one sensor in your array for effective analysis.
You mentioned a few specific sensor technologies. Let's maybe zoom in on some of the more important ones. You mentioned metal oxide microarrays with gradients. That sounded pretty sophisticated.
Yeah, that's a clever approach to get a lot of different sensor responses from a single small chip.
Okay.
Imagine taking a thin film of a metal oxide material and dividing it electronically into many small segments using electrodes. Now, the trick is how they make these segments behave differently. One way is to put a very thin gas-permeable membrane over the metal oxide, but make the thickness of that membrane vary across the chip.
A gradient in thickness.
Right. Another way is to create a controlled temperature gradient across the chip, so different segments are operating at slightly different temperatures.
Ah, okay.
Since both the diffusion through the membrane and the reaction rate on the metal oxide depend on thickness and temperature, each little segment effectively acts like a slightly different sensor. When different gases or odors hit the chip, you get a unique pattern of electrical conductivity changes across all those segments.
So it's like having a whole mini team of specialized sensors built right onto one tiny chip. Very neat.
It is. It allows for miniaturization while still getting diverse responses.
What about conducting polymers? I know you said those were used early on and are still researched.
Yes, conducting polymers, or CPs, were definitely in some of the first commercial e-noses, and they remain popular, especially in academic research. A big plus is that they respond to a really wide range of organic vapors, and they do it at ambient temperatures.
No heating needed.
Generally, no heating needed. And one of their key strengths is their versatility. Compared to metal oxides, there's a huge chemical diversity you can achieve with polymers. You can tailor their properties quite specifically during synthesis, maybe by changing the counterions or adding specific functional groups to the polymer backbone to make them more sensitive or selective to certain types of molecules.
So you can kind of design the polymer for the job.
To some extent, yes. Common examples you see are things like polypyrrole, polyaniline, polythiophene. They're often made electrochemically, which allows for controlled deposition as thin films.
But they have downsides too.
They do have some shortcomings. They can sometimes have longer response and recovery times compared to MOS sensors. Their signal can sometimes drift over time, meaning their baseline changes. Reproducibility between sensors made in different batches can sometimes be an issue, and they can be sensitive to humidity and oxidation, which can affect their performance.
So trade-offs as always.
Always trade-offs. But despite these, advances in microfabrication are enabling larger, more sophisticated CP arrays, often integrated directly with control electronics. And they're finding use in areas like food and beverage quality monitoring, assessing sewage odors, monitoring agricultural smells, and even in medical and veterinary science.
And the more traditional metal oxide semiconductor MOS sensors, you mentioned they were early players and still common.
Yes, MOS sensors were among the first used, and they're known for having generally good sensitivity, especially to polar analytes like alcohols, ketones, etc.
Yeah.
And as we mentioned, you can tune their selectivity somewhat by changing the operating temperature or by incorporating tiny amounts of noble metal catalysts like platinum or palladium into the metal oxide material.
But the drawback is the heat.
The primary drawback has historically been that they need that heating element to get them up to operating temperature, sometimes several hundred degrees C. That means higher power consumption compared to, say, polymers or SAW sensors.
Which isn't great for portable devices.
Exactly. However, there's been a lot of progress. Companies like AirSense Analytics, for example, have developed multi-sensor chips that integrate multiple MOS sensing elements with microheaters on a single silicon chip, significantly reducing size and power needs.
So they're getting smaller and more efficient. Any other issues with MOS?
They can sometimes be susceptible to poisoning by certain compounds, particularly sulfur-containing compounds, and some weak acids, which can permanently degrade their performance.
Oh.
But despite the drawbacks, their maturity, potential for low-cost mass production via semiconductor techniques, and good sensitivity mean they are still very commonly used in commercial e-noses. And the potential for microminiaturization is huge. NIST, for example, did work using microheater arrays where they could rapidly vary the temperature of tiny sensor elements, creating lots of virtual sensors from just a few physical ones.
Virtual sensors again. That's clever.
Yeah, significantly increases the information you can get. MOS sensors are used for detecting toxic gases, volatile organic compounds, VOCs, and many food-related species like spoilage indicators.
Okay, so we've covered the hot MOS sensors and the cold conducting polymers.
Yeah.
What about things like electrochemical sensors and MOSFET arrays? Where do they fit in?
Electrochemical sensors, the kind often used in specific gas detectors, like for carbon monoxide, can be used in e-noses. However, they often lack the broad range of sensitivities needed for a general-purpose smell detector. They might only respond strongly to a few specific gases. Plus, they can have issues with sensor lifetime and sometimes challenges with integration and microminiaturization. So you tend to see them more in specialized applications or as part of a hybrid array.
Okay. And MOSFET arrays.
MOSFETs, metal oxide semiconductor field effect transistors, have also been explored for ENERS arrays. Usually, the gate material of the transistor is coated with a catalytic metal like platinum, palladium, or iridium.
And different metals respond to different gases.
Generally, yes. Palladium is good for hydrogen. Platinum or iridium might be used for ammonia or ethanol. There's also work on chemfets for sensing in liquids. But a common limitation is that MOSFET gas sensors often have relatively low sensitivity to many important volatile organic compounds. So, like electrochemical sensors, their use in broad-spectrum ENOs is somewhat limited, often finding a niche in hybrid arrays or specific applications involving gases like hydrogen, ammonia, or ethanol. Linköping Institute in Sweden did a lot of pioneering work here.
Got it. And what about some of the other sensor types we touched on? SAW sensors and optical arrays?
Right. Surface acoustic wave, or SAW sensors, applying pattern recognition to data from SAW sensors and their cousins, quartz crystal microbalances, QCMs, actually goes way back to 1986.
Really? That early?
Yeah. Today, SAW sensors coated with various sensitive polymer layers are widely used in electronic noses. They offer very high sensitivity, they work at room temperature, and have low power consumption.
Sounds like a good combination.
It is. But again, their advantages and disadvantages are often linked to the properties of the polymer coatings. Use things like selectivity, stability, and humidity sensitivity depend heavily on that coating material.
And optical arrays, how do they work?
Optical sensor arrays often use fluorescent dyes. Imagine tiny polymer beads, each containing a specific fluorescent dye attached to the ends of optical fibers.
Okay.
When volatile vapors are absorbed into the polymer beads, it can cause changes in the fluorescence, maybe the intensity, the color, or how long the fluorescence lasts. These changes are measured using light detectors.
And different dyes respond differently.
Exactly. By using an array of beads with different dye polymer combinations, you get a pattern of optical responses. It's actually been compared to mammalian olfaction because of the diversity of receptors. Advantages include potential for speed, small size, and diverse coatings. Disadvantages can include the complexity of the optical readout instrumentation and the fact that fluorescent dyes can sometimes degrade over time due to photobleaching.
Interesting, like tiny glowing smell detectors.
Kind of. There are also colorimetric arrays, using spots of chemicals like metalloporphyrins that simply change color when they bind to volatile compounds. You read the pattern of color changes, maybe with a camera.
A non-electronic, electronic nose.
Yeah, in a way. Though processing the image is electronic, these also face challenges with stability and instrumentation.
It really sounds like there's a whole toolbox of different sensor technologies available, each with its own strengths and weaknesses.
That's absolutely right. Metal oxides, polymers, SAW, optical, electrochemical, MOSFETs, even less common ones like calorimetric sensors or cantilever-based sensors.
Which naturally leads back to the idea you mentioned earlier, combining different types into hybrid arrays. Why is that beneficial?
Well, precisely because each individual sensor type has limitations. By combining sensors from different classes, say a MOS sensor, a polymer sensor, and a SAW sensor in the same array, you can potentially overcome the weaknesses of any single type and leverage the strengths of each.
Getting the best of multiple worlds.
That's the idea. It's been observed pretty consistently that combining sensors from different classes often yields more effective data for telling samples apart than just adding more sensors of the same class. They provide more chemically independent information, making the array more versatile.
So you can tackle a wider range of smells.
Potentially, yes. Hybrid e-noses allow you to select sensors based on the specific challenges of the sample you're analyzing. You see commercial systems combining MOS and MOSFETs, or MOS, QCMs, and electrochemical sensors. It's a way to build a more robust and capable sniffing system.
So the sensor array, whether homogeneous or hybrid, is clearly a critical piece. But you also mentioned the system needs a way to get the sample to those sensors reliably and then get ready for the next sniff. That's the sampling system, right?
Absolutely. You can have the best sensors in the world, but if your sampling system is inconsistent or introduces errors, your results won't be reliable. It's arguably the third vital component, alongside the sensors and the pattern recognition.
What's its main job?
It has a couple of key roles. First, it has to collect a representative sample of the air or gas headspace you want to analyze and deliver it to the sensor array in a controlled and reproducible manner. Second, after the measurement, it needs to help restore the baseline conditions, usually by purging the sensors with clean air or an inert gas, getting them ready for the next measurement.
So consistency is key.
Hugely important. A good sampling system works to minimize variations caused by external factors, things like fluctuations in ambient humidity, temperature, or even the overall concentration of the sample vapor. You want the only significant variable affecting the sensor response to be the actual composition of the odor itself.
Does it do anything else? Like pre-processing?
Yes, it can perform pre-processing steps to enhance the quality of the data the sensors see. This might involve filtering out particulates, controlling humidity, or even pre-concentrating the sample to boost sensitivity. The goal is always to optimize stability, reproducibility, signal strength, and response speed.
Has there been much research on optimizing these sampling systems?
It's interesting. Despite demonstrations showing that an optimized sampling system can significantly improve Eno's performance, it's arguably received less research attention compared to sensor development or pattern recognition algorithms. Although many systems automate the process for handling series of samples.
That's surprising. So how do they pre-concentrate the sample?
Several techniques are used. Purge and trap is one, where you bubble a gas through a liquid sample or pass it over a solid sample to release volatiles, trap them on an adsorbent material, and then thermally desorb them in a small volume of gas to send to the sensors.
Okay.
Another very common one, especially borrowed from GC, is solid phase microextraction, or SPME. This uses a small fiber coated with an adsorbent material. You expose the fiber to the sample headspace, the volatiles adsorb onto it, and then you introduce the fiber into the eNose inlet where the volatiles are desorbed, usually by heating.
SPME sounds quite neat and simple.
It is versatile. It's even been used creatively as a kind of filter, for example, using a specific SPME fiber to selectively remove ethanol from a sample before it hits the sensors, preventing them from getting overwhelmed or blinded by the high alcohol concentration.
Clever. Like sunglasses for the nose.
Hey, yeah. There are commercial systems that use adsorbent tubes, similar to SPME, coupled with thermal desorption, sometimes even with a small GC column for pre-separation before the sensor array. Others have used catalytic combustors before the sensors to convert certain sample components into compounds that are more easily detected by the specific sensors being used.
Wow, lots of tricks. What about the chamber where the sensors actually sit?
The measurement chamber itself is also really important. The materials used have to be carefully chosen to be as inert and non-adsorbent as possible. You don't want the chamber walls grabbing onto molecules from one sample and then releasing them during the next measurement that causes memory effects.
What materials work best?
Things like glass, fused silica, stainless steel, and PTFE, Teflon, are commonly used. But each has pros and cons regarding inertness, ease of machining, and cost. The volume and geometry of the chamber also matter. You want good flow dynamics to ensure all sensors are exposed uniformly and quickly to the sample vapor. There's been work on optimizing chamber designs for better performance.
So a lot goes into just getting the smell to the sensors properly.
It's a critical and sometimes underestimated part of the whole system.
Okay, so we've got a pretty good handle now on how electronic noses are built and how they work, from sampling to sensors to software. Let's switch gears a bit and talk about why they're actually useful. What are the big advantages they offer in the real world?
Well, one of the fundamental benefits is that electronic noses approach aroma distinction holistically, much like our own olfactory system does. They don't necessarily need to identify every single chemical compound present to tell the difference between smells.
I get the overall picture, the gestalt.
Exactly. And because of this, they can work really well with both simple, pure compounds and also very complex, undefined samples, like the aroma of coffee or the smell of soil. Traditional analytical methods, which often take a reductionist approach, identifying individual components can sometimes struggle as the complexity of the sample increases.
That's interesting, like the sum is more than the parts for the eNose.
In a way, yes. There was actually a USDA effort over 3 years using GCMS to analyze grain odors. They found essentially no correlation between the detailed chemical composition they measured and the perceived odor quality. The overall pattern matters.
Wow, okay. And compared to, say, using human testers?
That's where the practical advantages really shine. Using human sensory panels, even when backed up by lab analysis like GCMS, is often incredibly time-consuming and expensive. You need trained panelists, controlled conditions.
And people get tired or sick or just have a bad day.
Precisely. Electronic noses can provide rapid, often real-time, and cost-efficient sensory-based analysis for things like odor, aroma, and sometimes even taste using related e-tongue technology. They can monitor things continuously over long periods without fatigue.
And they're objective.
Completely objective. They eliminate the inherent variability you get with humans, individual differences in sensitivity, adaptation, getting used to a smell, fatigue, health status, even mood can affect human perception. Plus, e-noses can safely analyze potentially hazardous or unpleasant compounds without risk to personnel.
So they're great for routine stuff, like quality control on a production line.
Absolutely ideal for routine use. And importantly, their results often show good correlation with both human sensory panel assessments acting as a sort of consumer-based instrumental test and with classical analytical methods like HPLC or GCG-CMS, but they're usually much, much faster. You mentioned e-tongues. They can analyze caffeine much quicker than HPLC, for example.
Faster, cheaper, more consistent. What about sensitivity? How do they compare to the human nose?
Often, they can be incredibly sensitive, sometimes even exceeding the sensitivity of the human nose for specific volatile compounds. We have data showing detection limits in the parts per billion or even parts per trillion range for certain analytes with specific e-nose types.
So they can potentially pick up things we can't even smell.
Potentially, yes. They might be able to differentiate subtle top notes versus middle notes in an aroma profile, and they have the ability, like we discussed, to store these odor or aroma fingerprints in databases, creating a kind of objective digital olfactory memory.
Those are some pretty compelling reasons to use them. It sounds almost too good to be true in some ways. Given all these advantages, what are the limitations? What's still holding them back or making it challenging to use them in every single situation?
Yeah, they're not magic bullets. There are definitely limitations. One is that they can sometimes lose sensitivity or become saturated if there's a very high concentration of one particular component in the mixture. Think the ethanol in wine, for example. It can swamp the sensors.
Binds them, like you said earlier.
Right. Another key point is that they typically provide comparative analysis and identification within their trained library. They don't usually allow for absolute calibration or quantification of unknown individual components easily.
So telling you what it is relative to knowns, but not necessarily how much in absolute terms without specific calibration.
Generally, yes. Sensor lifetime can also be an issue. Depending on the sensor type and the application, they might only last from several months to maybe a couple of years before needing replacement.
Okay.
And developing a robust method for a new application, training the library, validating the performance often requires significant upfront effort. It's not always plug and play for every new smell problem. Getting truly quantitative data about how different two aromas are can also be challenging.
And is it always clear what the e-nose is basing its decision on?
That's another subtle but important point. There can sometimes be ambiguity about whether the discriminations the e-nose makes are based on the key odorous components we care about, or potentially on other non-odorous volatile compounds that happen to be present and correlate with the odor.
So it might be picking up on a non-smelly marker that just happens to go along with the smell.
It's possible, yeah. Needs careful validation.
You also mentioned sensor drift and environmental conditions earlier as challenges.
Yes, sensor drift, where the response characteristics change slowly over time due to aging or gradual contamination, is a common problem that requires periodic recalibration. And environmental sensitivity, especially to humidity, is a really significant issue for many e-nose technologies.
Particularly the polymer ones.
Particularly polymer-based sensors, yes. Water vapor in the air can significantly affect their response, sometimes masking the response to the target analytes or causing spurious signals. If humidity changes aren't properly compensated for, it can lead to completely wrong classifications.
So managing humidity is crucial.
Minimizing the impact of humidity is a key design task for many e-nose instruments. Some systems try to control it, use reference air measurements, or incorporate humidity filters. There's also ongoing development of sensor types that are inherently less sensitive to water vapor.
And reproducibility. Getting the same answer time after time.
That's another common and important challenge. It's affected by both sensor aging and poisoning, like we discussed, and also by variations in the sampling process. Using automated sampling systems that control temperature, shaking, and equilibration time can definitely improve reproducibility for things like headspace analysis.
But those add cost and complexity.
They do tend to be bulkier and add cost, yes. Although, again, there are efforts to miniaturize these automated sampling systems as well.
It seems like the field is constantly trying to address these limitations. You mentioned integrating multiple sensor types earlier.
Right, that's one trend. Companies are increasingly putting multiple measuring principles into a single instrument to get a more robust picture. Alpha MOS, for example, has combined fingerprint mass spectrometry with metal oxide sensors. Others have integrated quartz crystal microbalances with MOS sensors for monitoring food packaging odors, or combined MOS with conducting polymers for medical applications like detecting amniotic fluid leakage. The hybrid approach is definitely gaining traction.
Despite these hurdles, it really sounds like electronic noses are finding their way into a lot of different markets. Where are we seeing them used most right now, and where do you see the biggest potential for growth?
The markets are incredibly diverse, and they are definitely expanding. A lot of the growth is driven by the possibilities for improving industrial processes, agricultural monitoring, quality control, and generally enhancing our living conditions.
Makes sense.
The food industry is a huge area. Using e-noses for quality control checking freshness, detecting spoilage in products like fish, meat, milk, tomatoes, wine. Verifying authenticity is this really extra virgin olive oil, detecting contamination or mislabeling, comparing production batches to a reference standard, potentially replacing or supplementing human taste panels in some QC roles, measuring shelf life, even evaluating how packaging interacts with the food product over time.
That food safety aspect seems really important.
It is, especially thinking about, say, elderly populations whose own sense of smell might be diminished. Ensuring food freshness is critical.
What about outside of food?
Lots of other industries, too.
Huh?
Analyzing petroleum products, detecting explosives, environmental odor monitoring around factories or waste treatment plants, quality control in the automotive industry, checking for interior material off-gassing, even monitoring milking systems on dairy farms or analyzing raw materials for cosmetics.
Wow. And you mentioned medicine and space.
Yes, those are really exciting frontiers. There's a lot of research into analyzing human breath, sweat, urine, even stools for patterns of volatile compounds that could indicate diseases like cancers, infections, or metabolic disorders. Companies like Aromaskin, Bloodhound Sensors, EEV have worked in this space. It's still largely research, but the potential for non-invasive diagnostics is enormous.
Breath analysis for disease. That's fascinating.
Isn't it? And in space exploration, NASA has used e-nose technology, like the e-nose developed at JPL, to monitor the air quality aboard the International Space Station, looking for harmful contaminants.
Keeping the astronauts safe.
Exactly. So the potential impact is really broad. Healthcare, environmental monitoring, indoor air quality, process control, safety and security, military applications. It's hard to imagine an area where better chemical sensing wouldn't be useful, and new applications are emerging constantly.
It's amazing to see such a wide range of applications already. Could you give us maybe a few more concrete examples just to illustrate the versatility?
Sure. Looking through some studies, they've been used to discriminate between different varieties and roast levels of coffee beans, identifying the quality grade of paper used in packaging, assessing meat freshness, and predicting shelf life in the meat industry. Monitoring fish freshness is a classic application, identifying and classifying different perfumes and flavors, sorting fruit juices based on quality or origin. As we said, monitoring environmental malodors from various sources, detecting fires, even identifying the type of material burning, early warning systems for electrical fires based on overheating components. The list goes on.
It really covers a lot of ground.
It does. And it's important to remember the presence of those traditional analytical instruments like GC and MS doesn't really limit the market for e-noses because they're often designed for different tasks.
Right, different tools for different jobs.
Exactly. You still need the high-cost, complex instruments operated by skilled personnel when you need detailed qualitative and quantitative analysis, when you need to know exactly why two samples are different down to the molecular level. But for rapid quality tests, routine screening, monitoring processes, or detecting gases that might be irritants but not strongly odorous, the e-nose is often a much better fit.
Faster, cheaper, easier for those kinds of tasks.
Precisely. So the possibilities are excellent across numerous application areas. These kinds of intelligent sensing systems are playing a key role in industrial modernization and environmental protection efforts.
This has been a truly eye-opening deep dive into the world of electronic noses. Really fascinating stuff. To try and bring it all together, what are the key takeaways you think our listeners should remember from our chat today?
Well, I think we've seen how electronic noses really emerged as a response to the limitations of both our own senses and traditional lab methods for analyzing gases and smells.
Right, filling a specific need.
Yeah. Their core technology relies on using arrays, or teams, of partially selective sensors combined with sophisticated pattern recognition software to interpret the collective response.
The smell signature idea.
Exactly. We've touched on the wide variety of sensor technologies being used from the established metal oxides and conducting polymers to newer approaches like SAW-W sensors and optical methods, each with pros and cons.
And the growing number of places they're being used.
Definitely. The applications are already diverse and expanding rapidly across food, environment, medicine, industry, and safety. We also talked about the ongoing challenges, things like sensor drift, humidity sensitivity, and the need for careful calibration and method development, but also the continuous progress being made to overcome these hurdles, like using hybrid arrays and smarter algorithms.
It's clear that electronic noses offer a really powerful and versatile tool. They give us rapid, cost-effective, and objective analysis in many situations where traditional methods or even our own noses just fall short. It really is exciting to think about the impact this technology could have moving forward.
It absolutely is. And maybe that leaves us with a final thought for you, the listener, to ponder. As this sensor technology continues to get better, smaller, cheaper, and as the pattern recognition algorithms become even more sophisticated, how might electronic noses fundamentally reshape our interaction with the world around us?
Yeah.
Imagine them guaranteeing the safety and quality of virtually all our food, or providing doctors with instant, non-invasive diagnostic tools for detecting diseases in their earliest stages, or even acting as a distributed network monitoring the health of our entire planet's atmosphere. The potential applications are truly transformative.
A lot to think about there.
Yeah.
Definitely encourage everyone listening to explore the specific areas that sparked your curiosity today.